Last time we have started to study fermions, and we have seen how to treat them in flat space. Have seen how to relate the Lorentz transformations to the transformations on the fermions themselves by means of the group SL2C. Now we move to the coupling to gravity. So everything we have written so far by means of space-time indices now will be understood by means of flat space indices. All formulas we have written hold, but now we have to do something more to couple the theory to gravity. So now we are considering Lorentz transformations. They look like the change of basis, as we have already seen. It depends on the point, on the space-time point, but it is not the most general change of basis, but local Lorentz transformation. What do we do with that? So the question is now how to embed the Dirac action into gravity. Recall that d slash partial slash is gamma mu partial mu. Well, I write the result and then I tell you what it means, what it is. The action becomes as follows. The integral on the manifold of E d4x. We'll give the definitions in a moment. Psi bar gamma A, actually let me maybe factorize it there, E mu A partial mu plus a certain connection psi. And if you want, you can add the mass term that's easier, psi bar psi. Well, first we want to generalize this, and okay, partial mu, the partial derivative will go into some, we will see covariant derivative, and we will see later what that is. Second, we cannot contract this index with a space-time index because we want gamma matrices that are numbers, and they should know nothing about the point, should not depend on the point. And so to build a gamma mu that depends on the point, we use the gamma A flat space indices, which are the ones we have introduced last time, which are the usual numerical gamma matrices built last time with the Pauli matrices sigma mu and the sigma mu tilde. Those are those, gamma A are those, and we have an object to turn a flat space, a space-time index mu into a flat space index A, that is the Filbine, the inverse. So that's it. That's what we do. What is E? E is the square root of minus g, but it is here written as the determinant of the field by itself. So everything here is written into by means of the field by. So let us recall that G is equal to the determinant of G mu nu, but G mu nu is equal to E mu A eta A B E B nu. So you see that this is the determinant of the product of three matrices, and so it's the determinant of this times the determinant of that times the determinant of that. But the determinant of EA mu is what we call A, the determinant of eta is -1, A. So minus G is equal to E squared, where E is the determinant of the field by. Takes care of the minus sign as well. So that means that this object here is invariant under diffeomorphisms. And here also, we should check that these objects are scalars and they are invariant under local Lorentz transformations. They should be invariant under local Lorentz transformations. And this can be achieved, we will show, by defining this omega tilde mu as sigma AB omega mu BA, where omega mu BA is the spin connection, and sigma AB is -1/2 the commutator of two gamma matrices. Sigma AB, we had defined it already, right? Yes, here it is, -1/8. Can repeat it here. Gamma A, gamma B. Okay, so this is the trace of sigma omega, where sigma is this matrix with spinorial indices, and omega instead is the spin connection. This is the action, and we want to show that it does transform correctly, both under diffeomorphisms and under local Lorentz transformations. Diffeomorphisms. Diffeomorphisms, we already know that E prime, X prime, D4, X prime, this is the square root of -G, so this transforms correctly. Then a fermion, psi, under diffeomorphisms, diffeomorphisms are changes of coordinates. Since it has no space-time indices, mu, nu, rho, it does transform like a scalar. Like a scalar. And psi bar as well, because psi bar is psi dagger gamma 0. So psi bar prime x prime is equal to psi x. Then we also know that what? Partial mu prime transforms as a vector. So that is partial x nu, partial x mu prime, partial nu. E A mu prime, again, this has one index, upper index mu, so it has to transform like this. When you consider diffeomorphisms, you ignore flat-spaced indices and you ignore all indices which we do not write explicitly, which are those of the fermions. You just don't act on that, because on those indices the local Lorentz transformations do act. Omega mu A B prime x prime, same thing, like a vector. Which means also that this tilde, the tilde, is simply omega with some matrix that's invariant under diffeomorphisms, because it has no space-time indices. And so you also have this. And then it is easy to see that the action is invariant, because this is invariant, psi bar psi is invariant, this is invariant. Here you have a Jacobian, but you have a Jacobian also from the mu indices there, which is the inverse Jacobian, and nothing else. So what you obtain is that S prime prime x prime psi bar psi x prime psi prime x prime, and then if you want you add also the master, which conventionally has a minus sign. Psi bar prime x prime psi prime x prime, that is equal to S. Just replace every ingredient with its unprimed version and you will see all Jacobians compensate one another, and so the result is exactly S. Local Lorentz transformations instead act on indices A, flat space indices A, and on the spinorial indices alpha, because we know that on spinorial indices it acts with this matrix curly A, and instead on the flat space indices it acts with lambda. So lambda is a local Lorentz transformation, and that means that if you have an object like, for example, E. So this, now we are considering these transformations, local Lorentz transformations. Perhaps it's better to repeat it. So E mu A prime x, if you want prime, is equal to lambda A B E bu E B mu of x, but you also have x mu prime equal to x mu, because you don't change coordinates. So we will not write x prime at all now. This is the transformation, and then you will have psi prime x prime, if you want. That is curly A psi of x. And curly A is related to lambda AB by the formulas we derived yesterday. Now, you know that since E is the determinant of this matrix, when you transform, you can write the determinant in a Lorentz invariant way. It is certainly invariant under the components, the component of the Lorentz group that contains the identity. And therefore, E prime is equal to E. The determinant doesn't change. Well, we also know that psi bar prime is equal to psi bar E curly A to the minus 1. So certainly this object, the mass term, is invariant as it was in flat space. There is no real difference here. The difference is in the kinetic part, because there is a derivative. And so when we transform that part, we must be careful, and we will have to check that this connection, as we have defined it with these gamma matrices, sigma matrices there, transforms correctly. So let's see how it should transform first to have an invariant action, and then we will see that indeed omega tilde transforms in the required way. So now I consider just the kinetic action. And we want to check what happens of sk prime. So as I said, E and E prime are the same, x and x prime are the same. Here we have E mu A, we have a lambda with lower indices, so you just lower the indices there, which means that you have a lambda A B B. Then you have psi bar. Psi bar goes into psi bar curly A to the minus 1. Gamma A is invariant. Gamma A is a set of numbers, so you copy it. And then you have partial mu, it stays. Then you have possibly a transformation of this object, because this is a connection, so who knows? And psi is curly A, goes into curly A psi. Okay, so this is what you get. Let's write it a little bit better. I integral of E d for x E mu b lambda AB psi bar curly A gamma A. And then let me act by means of the partial derivative on A psi. So I will have two terms, d mu curly A psi plus A partial mu psi. And the rest I copy psi. Now, it is easy by manipulating these things to check that the transformation, we write the transformation and then insert it back to check that it is the right one. Omega tilde prime, if you want, let's view it as a form. We do not need to write the index mu because Lorentz transformations do not care about that. It transforms as a connection, very similar to the transformations we know for a connection, but with this curly A instead of the omega, capital omega we used to. So let's check that then these two are indeed equal. So then Sk prime is equal to what? Psi bar, curly A to the minus 1, gamma A, partial mu curly A psi, plus A partial mu psi, then we replace that omega tilde mu prime times A. When we multiply by A to the right, here we have curly A omega, and then whatever remains plus curly A partial mu, omega mu, here we have the index, curly A to the minus 1, and then we have A and psi. Here the parenthesis is not there, but there. A and psi. Now, check these two terms, this one and this one. These are opposite to each other, as you know very well by now that by means of the famous partial integration, when you have a derivative in between the product of a matrix and its inverse, you can turn it around, changing the sign, and act on the other matrix, and then A minus 1A gives 1. That means that this term cancels the other term there, and now you remain with what? So psi bar A to the minus 1, gamma A, then I can factorize an A, curly A, partial mu plus, this is a tilde, omega mu tilde psi. And now we have just Sk, because you should remember that the matrices, the gamma matrices are precisely those matrices that satisfy an identity that we wrote in many equivalent ways. One form, the same as in flat space, by the way, so this identity is the same that we used in flat space. This is precisely gamma B. So we reduced the proof of invariance to the proof we had in flat space, as long as this transformation law holds. So that should be true by itself, and it is indeed true, and we will now show it. Because we know everything about this omega, the spin connection, and we know how the spin connection transforms. And that's just multiplied by some gamma matrices which do not transform when you transform everything, every indices, so somehow they do, somehow they don't. We want to prove this identity. What do we know? Well, for example, we know the transformation of omega, which is lambda, omega, lambda to the minus 1, plus lambda, d, lambda to the minus 1. This is the generic transformation for a connection. And instead of the capital omegas, we have lambda because our transformation is not a general linear transformation, it is a local Lorentz transformation. Then we also know that the definition of omega tilde is this trace of sigma omega, which means sigma A B omega B A. And so now it's just a matter of copying, and then there is a certain work to do to prove. It's not particularly complicated, but we do it in detail. So, omega tilde prime is the trace of sigma omega prime. Sigma doesn't transform, sigma numbers. So can only transform omega prime. Omega prime, we know that it transforms like that, and we want again to show that when you transfer from the indices of flat space indices to the spinorial indices, lambda goes into A, curly A, basically. It's like doing this replacement. Well, omega prime is this. So here we have two contributions, sigma lambda omega lambda minus 1 plus sigma lambda d lambda minus 1. If you want, I can write this. Like that. And we would like this to be equal to e to the minus 1 omega a curly a to the minus 1 omega a plus curly a d curly a to the minus 1. And not surprisingly, the first term will be equal to the first term, and the second will be equal to the second term. So we need to prove that the first goes into the first, and the second goes into the second. How do we do that? So the first is we can consider the first thing there. And since it is a trace, by the cyclicity of the trace, that is also trace of lambda to the minus 1 sigma lambda omega. And let's consider lambda to the minus 1 sigma lambda then, AB. That will be equal to lambda to the minus 1 AC sigma CD lambda dB. And we know that sigma is minus 1/8 of commutator. There it is. That's equal minus 1/8. Let's replace this with a commutator. Lambda dB. But then we use the property here, which can be written in many different ways. And for example, one way was this. So a gamma times a lambda, it's a gamma, you see. That's gamma contracted with a lambda. Lambda minus 1 is also simply related to lambda. That's, again, gamma contracted with a lambda. So what you get there is A gamma curly A to the minus 1. Here the index is lowered, but if you want, you can raise it. Then you lower this and you raise that. You have precisely this formula, which means that then you have to lower the index on the right-hand side. And the same thing here. So when you do that, what you get is just minus 1 divided by 8, curly A gamma A curly A to the minus 1, curly A gamma B curly A to the minus 1. But then curly A to the minus 1 times curly A gives 1 when they are in between, and the others also in the commutator. So this is just curly A sigma curly A to the minus 1. Then it's easy to show that this is precisely curly A omega tilde curly A to the minus 1. Why? Because this is that, and because these matrices A curly A have nothing to do with omega, because omega has no spinorial index. So the trace is on what indices? Remember, the trace is on flat space indices. The flat space indices are here and here, yes. But these matrices have nothing to do with flat space indices. They act on the spinorial indices, and they are the only ones that act on spinorial indices. So check it. Oh, there is an a to the minus 1. Maybe I got... No, yes, this is a to the minus 1. This is the rule for the transformation lambda to the minus 1. A to the minus 1. A to the minus 1 is to the right and A is to the left. So a to the minus 1. That's what we need, and indeed that's what we get. The other one is a little bit more tricky. But we can do it because there is a proof that is relatively simple. It involves some identity, but once we have done it, so let's do it. It takes less time than talking about it. So now we want to show that the trace of sigma lambda d lambda to the power minus 1 is equal to a d a minus 1. Again, let's remember that gamma a lambda a b is equal to curly a gamma b curly a to the minus 1. And what we have to do is to first use it is simpler to use the usual partial integration to move the derivative on lambda instead of lambda minus 1. Well, that's not necessarily that useful because lambda minus 1 is very simply related to lambda. But anyway, let's do it. Then we replace, so there is a minus, sigma with its definition, minus 1 over 8, and then the trace. So you have gamma A, let's write it. So gamma A, gamma B, minus gamma B, gamma A. And then the trace means that you have to contract these indices, all of them CA. Yes. This is explicitly what the trace means. So sigma d lambda minus 1, sigma AB d lambda BC lambda minus 1 CA. Now, let me write it in a form that highlights these objects here, or some similar thing with lambda to the minus 1. So for example, here you have 1 over 8 lambda to the minus 1 CA gamma A. And here you have gamma B d gamma B lambda BC. I can write it this way because gamma B is constant, so I can place it inside the derivative, and therefore you see that this object is precisely that object, and the same will be for this one because of the relation between lambda minus 1 and lambda itself. Okay. This for the first term. The second term is minus the same thing, so you have a commutate. Minus the same thing. Now we can replace these objects there, again, as in the previous case, by curly A gamma curly A minus 1. And check it yourself with lambda minus 1. Remember, the lambda minus 1 is lambda itself with indices exchanged, so that's easy. So you have 1 over 8 curly A, gamma A, curly A minus 1, D, curly A, gamma B, curly A to the minus 1. And the difference with respect to before is that there is this D. So you have to compute the D. The D acts both on A and A minus 1. So we have to do it. So 1 over 8, first contribution, A, gamma A, A minus 1, times the derivative. That is dA gamma B, A minus 1, plus A gamma B, dA minus 1. And this is the first part of the commutator, then you have the other part. Minus, you commute the two things. And that appears to the right, curly A, gamma A, curly A to the minus 1. I will just write down the various terms. Let's check first this one and that one. So this multiplied by that, you see that A to the minus 1 go away. Sorry, these indices are not A and B, but C and C, or A and A, if you want. They are equal, because the index here remains C, and the index there remains C. So you can call the way you like them, but they are equal. So A, and A. So these two terms I was saying, you see you have A, gamma A, A minus 1, A, gamma A. Remember there is an identity for gamma matrices that says that this is 4. So you have a 4. Moreover, these two I'm considering give the same, well, okay, so 4, 1, 8 times 4 is 1/2. And so you remain with curly A, D, curly A to the minus 1. From the other one, there is a minus 1/2, D curly A to the minus 1. Then these are again equal by a partial integration. The other terms go away, and we'll show now that the other terms go away, and this is the end of the proof. Okay, because we want to show this. So these two terms are equal, and they give that. The other two terms I have not written so far just disappear. So the other two terms are this one and this one. So let me write them. They are equal, I think, to each other. So 1 divided by 8, curly A, gamma A, curly A to the minus 1, D curly A, gamma A, curly A to the minus 1, minus A gamma A, whatever it is, it doesn't really matter because there is an identity that kills them all. just copy it, A. So this is 0, this is 0, the other two are equal by partial integration. You can move this derivative there and change the sign. Why are these 0? Again, they are the same thing if you use a partial integration. Why are these 0? Because this object is 0. And why is this 0? Because this object is 0. Why? Remember that sigma is a commutator of gamma matrices. Well, we have an identity for gamma matrices that says that when you multiply two gamma matrices by gamma A and gamma A contracted, you get something that is symmetric. You get eta. And sigma is antisymmetric. It's a commutator of two of those, so you get 0. So we just have to show that this thing here implies that thing there. And that is not so difficult. It's a trick similar to what something we did yesterday, the other time. First of all, let's recall what curly A is. Curly A is the exponential of the trace of sigma t. And then I can use an identity which is similar to the Campbell-Baker-Hausdorff formula, which you might find useful in some other cases, which is this identity here, e to the minus m d e to the m. There is an expansion for this expression. That is equal sum from n equals 0 to infinity minus 1 to the power n divided by n plus 1 factorial. And then you have m commutator, m dm. N commutators. It's a long, you can just write the exponentials as series and check this formula. So basically it is dm minus 1 over 2 factorial m dm plus 1 over 3 factorial m dm plus etc. So you want a to be e to the minus m, a to the minus 1 e to the m, but a is equal to e to the trace of sigma t, and so that means that m is equal to the trace minus the trace of sigma t. Now the trick is to show that here you see, here you have, in this entire expression, you have gamma A and gamma A to the left and to the right. You just need to show that all these terms are sigma, 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 sigma. They are all sigmas. And this is very easy because, well, this is a sigma. In gamma matrices, that's a sigma. T has no index, no spinorial indices. And this is a commutator of 2 sigmas, which is a sigma. And the commutator of 3 sigma is a sigma, and so on and so forth. Maybe we continue later, but the commutator of 2 sigma matrices is a combination of sigma matrices because these are just the generators of the Lorentz group, apart from effect. So let's pause it 10 minutes and then we continue.